Hello everybody, this is our lesson on waves, and I have notes for you, so please check them through your lesson. I solved a few questions, just the paper written notes, and I will also do a video on solving some of the questions as well, explaining step by step. But here are the waves. So there are different types of waves, and we're gonna look at three types of waves through this course, physics course. Mechanical waves, they can be longitudinal or transverse. So longitudinal waves, if you can imagine, I'm going to use the heart. If you can imagine little heart right here, if you compress and stretch the spring, which way would the heart move? Would it move up and down, or would it move left or right? And I guess your answer would be left and right. So this heart would be, it doesn't move through the spring. So the heart is like matter inside of the spring. It's just the stuff inside of the spring. So every single point on the spring in the longitudinal wave will be moving left and right with the motion of the wave. And in the spring, you will have compressions and expansions. So where you have compression, it's like almost having the high density. So it's like top of the wave. And when you have expansion, it's like having the low density, the bottom of the wave. So from high density to high density, it's called the wavelength. So if you took a ruler and you measured the distance between this point, the highest density, to the highest density, that would be the wavelength. And it measured in meters. If you take, let me move this heart right here. So for longitudinal waves, the waves are moving left and right, or up and down if you stretch the spring vertically, but we'll only look on the horizontal in the regular physics course. So if you move the wave left and right, compressions left and right, your particles in the wave will move left and right. So your particles will move along with the motion of the wave, longitudinally. They move along with the wave. If you imagine and you can watch all the videos that I posted for you through the lesson. So if you imagine the rope and somebody shakes the rope up and down, then imagine this heart. Which way will the heart be moving in this case? And I hope you imagine that it moves up and down. So when the wave is moving this way, every single particle in the wave is moving perpendicular to the motion of the wave. So if you make one shake, the wave is going to start moving in that direction. But every single particle doesn't move through the wave. Every single particle in the wave moves up and down. So what the particles do, when you do the shake, we just did energy, you transfer energy to every single particle in the wave. And that every single particle passes the energy to the next particle and to the next particle and to the next particle. So the wave, it doesn't transfer the matter. The matter does not move. Matter stays where it is. Where I place that dot, that's where that matter is going to stay. Or this dot is that matter, and it's going to stay within that part of the rope. But what this dot is going to do, it's going to push the next dot, and the next dot is going to push the next dot. So all the waves, when the waves travel, what travels is the energy. You give the energy, you can give energy to a wave through vibrations, like you would have vibration this way, you would have vibration up and down here, vibration up and down, vibration this way. So the source of the waves is always, mechanical waves, is always vibration. And what moves through is it's not the matter, it moves the energy. Here is another good example for you. There are different types of waves that we're going to be looking at. So one of examples of longitudinal waves, if you think when I am talking to you, the air particles are being vibrated in my throat, and after that they're leaving my throat or mouth and coming out, and not every single molecule that comes out of my mouth is running into your ears, especially where you are now and I am. So we are on the other side somewhere of space. So what you hear is the vibration of the air that is transferred in all the directions longitudinally. So my sound waves are going to be a longitudinal type of wave, because the molecule that is vibrating out of the microphone right now vibrates the next molecule, and the next molecule vibrates the next one, and it actually goes in a circle in all the directions, because not only you can hear what I'm saying, but everybody around you can hear it too. So the energy that comes from the microphone being transferred all around the room right now until it gets lost within the walls, gets absorbed within the walls. So the sound wave is the longitudinal wave. Ocean waves on the surface of the ocean, they're not called transverse waves. They can be transverse waves, but they also called surface waves. Inside of the ocean can be longitudinal waves, because the energy is just transferred this way, unless it's like swirling. But we're not gonna ever talk about the ocean waves; they get more complicated. But transverse waves would be electromagnetic waves. It's the radiation that comes from the sun. And we're going to come back to it again later on. But there's something interesting about the waves that you need to know. So coming back right here, there are some characteristics of the waves. So the top of the wave, so this is the equilibrium line. So if there is no mechanical vibration that causes the wave to be disturbed, there would be no waves. It would be just flat surface. Imagine like water. It would be flat surface. In order for the waves to be present, you would have to start disturbance. You have to pass them energy to the matter. And how far, depending on how much energy you're passing, it will disturb the wave from its equilibrium. And how far it goes from equilibrium called amplitude. Amplitude measured in meters, because you just can again measure it with the ruler how far the wave is from its equilibrium. So that's the amplitude. And of course, the stronger the wave is, or the more energy the wave is, the stronger is going to be the amplitude. So the strength of the wave will depend on two things. One of the two things. One is amplitude. So the stronger wave will have bigger amplitude. Like let's say we're on the campus and I'm standing next to my room and I want to talk to you when you're standing on a different side of the campus. I can only talk to you if my voice is very loud. You would be able to hear me if the voice is very loud. Then when I produce the voice, it starts transferring through the molecules of the air. And as it transfers energy to this molecule, this molecule, this molecule, this molecule, eventually by the time it gets to the other side of the campus, you will barely hear what I just said, even though the amplitude was high, but the energy gets lost when it was transferred to you on the other side of the campus. So the higher energy is, the higher it's going to be the amplitude. The other way to make a wave of stronger energy, or give the wave energy, it's like these all have energies, right? We said the wave is the transfer of the energy. So the more vibration you produce, the more, let's say this way, the more shakes per second you make, the stronger the wave is going to be. So if I make just one shake, the wave is going to go and die. But if I keep making the waves will keep going more. So in order to make the waves stronger, or the energy of the wave stronger, you either make more of them, or you have to make it stronger as an amplitude of disturbance from the equilibrium. So the top of the wave is called crest, and the bottom of the wave is called trough. And the distance from the trough to trough is called the wavelength, and the wavelength is the distance, so it's measured in meters. Amplitude is the distance, how far disturbed. It's also measured in meters. And so I can measure, let me show you it here. I can say from crest to crest is my wavelength. Or maybe from this point to this point. You see this point on the wave and this point on the wave is exactly the same point. Or maybe from this point to that point. You see this point here is exactly the same point as that one. Or maybe from the point when the wave passes through the equilibrium going down, through the equilibrium going down. or maybe through the point where the wave goes through equilibrium up and equilibrium up. All these, including this one, are called the wavelengths. So you can measure wavelength from here to here, or from there to there, or from here to here, or from here to here. There are different ways. As long as you take same spot of the wave in a different position time. So it's not this time. So the wave is going to travel from here to here to the same position. Or maybe the wave is going to travel from this point to the same position on the other side of the wave. So this would be called wavelength and measured in meters. So that's just the length, because there's another thing that we're going to be looking at later that's called periods, and that's the time. So far, a few characteristics: crest, trough, amplitude, wavelength. The letter is, I believe it's Greek letter. It's lambda. It starts with L, lam, like M, lambda. Then, so here are a few more things about characteristics of the waves. One is period. So the period, like I showed you right here, this was how long is this part? That's the wavelength. Now, if I don't say how long, but I say how long is the distance. If I say how long does it take, what does it mean? How long does it take? How long does it take you to get to school? What am I talking about? I'm talking about time, right? So when I say how long it takes for the wave to go from crest to crest, I'm talking about the period. So if I look at the wavelength and I say, oh, how long does it take from this point to this point? That's a period. I don't care about how long it will take to that point. I need exactly the same point on the wave, but a different time. So how long does it take to go from this point to this point? That's the period. How long does it take from here to here? That's the period. So the time it takes, usually they have a definition of the period, the time it takes from the trough to trough or from the crest to crest, the time it takes, not how long the length is, but how long does it take to get from one point to another. Same point on the wave is called the period, and that is time. In other words, if it was a circular motion, how long would it take to go for the whole, to make one full circle completed? That's also period. So the period is how long it takes to complete one full oscillation. So from top to the top, from bottom to the bottom. So that's the time measured in seconds. Frequency. Frequency is the part, and usually it's going to be how many per second. So how many times can I shake my hand this way per second? That's how many waves I create per second. So I'll create one wave, two waves, three waves. So 3 waves per second gives you frequency equals to 3. And frequency is measured in hertz. So how many number per second is measured in hertz? So when you listen to your favorite station and it says, I don't know, like 900 something or 1000 something frequency in hertz, that is how many vibrations per second happens in order to produce that wave that you're catching on your radio. So again, period, the time it takes to make one revolution or go from crest to crest or trough to trough. Frequency, how many oscillations per second happens. Wavelength, how far it is from crest to crest if I measure in meters, like with the ruler, or from this point to this point, or from trough to trough, or maybe that point to this point. So that would be the wavelength. Amplitude is the disturbance of the wave. One more time. Wave is measured in meters. Amplitude is the disturbance of the wave, the distance away from the equilibrium, also measured in meters. Velocity. Velocity is always meters per second. So if you want to calculate the velocity of the wave, let me write it right here. So the velocity of the wave would be, it has to be meters per second. The only characteristics of the wave that I know that is in meters, that's related to the motion of the wave, is lambda, not disturbance, but the motion of the wave. It's lambda over time, which is the period. So this is in meters, this is in seconds, gives me meters per second. But the frequency and period have a reciprocal relationship. So frequency is equal to how many per second. How many vibrations can you make within the period of 1 second, let's say. So frequency is how many per second. So frequency is equal to 1 over t, or t is equal to 1 over frequency. So if I see right here, my 1 over t, I can rewrite it as frequency. And lambda is still right here. So I get my velocity is equal to lambda over t, meters per second, or lambda times the frequency. So there's two ways to calculate the velocity, lambda over t or lambda times the frequency. I did this example for you online, not online, in my notes. So let me explain to you here one more time. I have, I'm gonna make it maybe a little bit smaller here. Choose different color, do that one. Okay, so if I want to calculate the amplitude, and I'm gonna assume that every scale right here is 1 meter, how far is it disturbed away from the equilibrium? So I'm gonna count 1, 2, 3, 4, 5 squares. So my amplitude in this case is equal to 5 meters. Then I need to know what the period is. The period is from crest to crest, or from trough to trough. So if this one is 6 seconds and this one is 15 seconds, then my period is it 9 seconds? Right? Let me see. 10 seconds, yes. 2, 4, 6, 8, 10. 10 seconds, should be 10 seconds. My period is 10 seconds, and I should choose for period the correct letter. So let's do period is 10 seconds. So from here to here, 10 seconds. Not sure why it shows me. Maybe that's 14 and this 16. It's a little bit off. So the period is going to be 10 seconds. For the frequency, it's going to be 1 over the period. And that one is equal to 1 over 10, which is 0.1, and measured in hertz. And I'm going to do more questions solved for you online, like the videos, so you will be able to understand even better. There is going to be a different video. This is just the introduction to the basics of the waves, but I'm going to do a different video where I solve questions for you, where it's easier for me to write. I don't have to write it here on the screen. Let me go over something else here. These questions, maybe 10 questions I'll solve online, so you will have them there. Then let me see what else I have here. This is the review questions. The hard boundary reflections of the wave. So it can be hard boundary, soft boundary, low density to high density wave, high density to low density wave. So if you have a wave or the string attached to, it's called hard density, hard boundary. If it's attached and cannot move, every time the wave comes, it's going to be shifted, and it's called 180-degree shift. It's like complete reverse. So if the wave was coming this way and the boundary was hard, it will flip its direction. They say flip the phase or change the phase of 180 degrees and go this way. So that is for the hard boundary. For the soft boundary, so this one is able to move up and down. You see that the wave reflects back with the same phase. It doesn't change its phase. So if it was coming upward, it goes back upward. So for the soft boundary, if you have low density to high density, so I have thinner medium to thicker medium, some of the wave can be reflected, but because it's a harder density, the reflected wave has phase shift, and then it loses some of the energy to being reflected. So the amplitude of the wave that continues to the harder density is lower. So you see, like the one that was coming was stronger, the amplitude is stronger, but then some of it loosen up that way, and some of it cannot be as high as well because there's more matter. So there's more matter energy uses for every single molecule in the harder density. So here is how it goes from low to high density. And if you have from high density to low density, it's the same as having soft boundary. the wave does not change the phase when it gets reflected or continues going. Also because partially it loses energy back for the reflection, but because the energy that is left has to be distributed over less molecules, the wave can actually be higher amplitude when it continues. So this is important to know. Then there's such thing as superposition. If two waves are coming toward each other and they're in the same phase, so upward and upward, where they meet, there's going to be a superposition of the wave. So at that moment, you're going to hear like a higher beat or something. And also, I want you to look at this one. Do you see the big wave? It continues going. Do you see the little wave? It continues going in this direction. So they don't meet and go backward. They keep going wherever they were going. It's just at the moment when they meet, their amplitude spikes. Then there is constructive and destructive interference. So if two waves come in or meeting together and they're in the same phase, so at the same moment when they meet, so this wave meets this wave, the amplitude increases that way. If this wave meets that way, the amplitude is increasing. Its period does not change, so that means the time between here and here is still the same. So the time that they used to have is still the same, but its amplitude changes, so the strength, the more energy the wave has when it's combined. But if two waves are in opposite phases, so one is up and the other one is down, when they meet, they cancel each other. There's going to be like no noise at all. And again, you have a lot of videos that I posted for you through the videos on lessons that you can watch that part. Let me see if there's anything else right here. There's some interesting questions here I want you to go over. I don't want to make this video too long and see if you can answer. So here's the things that you need to know, and also these videos I posted online as well. So you can have refraction of the waves. So refraction means when it gets into a different medium, it cannot travel the same fast as it would travel in through this medium. So it will slow down, and that will change the direction of the wave a little bit. When it comes out back to the same medium, it goes back to the same direction. So the waves in different mediums travel at different speeds. If you think about it, there is three states that we know. They're not talking about the plasma, right? It would be solid, liquid, and gas. So if I was speaking solid, liquid, gas, where do you think the wave would move faster? Speed of the wave would be faster. Solid, liquid, or gas? Pause it maybe for a second and think. What do you think your idea would be? Where would the wave travel faster? Solid, liquid, or gas? So in solid, you have molecules standing next to each other very close. In liquid, the molecules are more farther apart, right? And in gas, they're even farther apart. So imagine I'm standing in our classroom and I'm trying to pass something from one side of the classroom to the other. If there are only a few people in the classroom, the first person takes something from me, has to walk, give it to the next person, has to walk, give it to the next person. And this is how I can pass information from one person to another. Now imagine where this would be in gas, right? There's only a few people in the classroom, that would be gas. So in order to pass the energy, you would have to walk in order to give energy to the next person, walk in order to give energy or a message to the next person, and so on. And this is how you would pass the energy or information through the classroom. Now in the water, we would have a little bit more people. Then in the water, I could pass the energy or the information, and the person would pass the information faster because the next person is sitting right next to the other person. But in the solid, we would be even more of us in the classroom, so it would be even easier to pass information. So as soon as I say to one person, the next person gets it right away because that person can pass it right away without even walking. So the same waves travel faster in solids, a little bit slower in waves, and the slowest would be in gas. And for mechanical waves to travel, you need medium. So I would not be able to talk to you in space because I cannot vibrate matter in space. There's no matter, or not dense enough, even if there's anything, to pass the information for you to get the vibration. So all waves, mechanical waves, need matter. So the air needs to be there for the sound to travel. Also, if you probably when you were little, you did this many times. When you sit in a water full, a tub full of water, and you go underneath the water, your ears can hear more in the water than you could hear in the air. Or if you ever not a good idea, but if you ever wanted to hear somebody talking on the other side of the wall, you can put your ear next to the wall and you would be able to hear the person. Also, another good example of hearing um, through the solids better when the train is coming. When the train is coming, you may not see the train coming and you may not hear the train is coming. But if you put your ear on the rails, you will hear the train is coming or not. So that's another way to keep safe yourself if you ever had to walk on the rails somewhere you don't want to be on the way of the train. You always check if the train is coming or not, if you're safe to be on the rails and walking. So there is refraction of the waves. There's reflection of the wave. And what's interesting, sometimes on standardized questions, they ask a question like the angle of incidence and reflection. So if this is the normal to the surface, then this angle is always equal to that angle. So this is angle of, this is reflection, this is incident angle. So incident angle is always equal to the reflection angle. Then absorption. This is the one that I was talking to you to the wall. So if I'm talking right now next to you, you can hear me. But if my voice is strong enough in your room and somebody is in the other room and they want to hear me, they can put an ear to the wall and they will hear everything that I'm saying. If my energy is pretty loud right now in your classroom or in your room, then they will hear the observed waves. They will feel the vibration that comes through the wall to the ear. And then refraction. You have seen probably the water waves when they're traveling and there is diffraction. The water waves when they travel and there's an obstacle on front of them. It can be just a hole or it can be a rock. So the wave kind of goes around that rock and meets on the other side. So that's called diffraction when there is an obstacle and it goes around the obstacle. So that part, and let me see. Sound waves. Sound waves depend on different things. Like we said, it's on material. So like, let's say in the air, this would be the speed of the sound waves in the air. If the air gets hotter, the molecules are already excited. They're jumping faster and faster. We talked about heat in the other topic, right? When we did thermodynamics. So the air at the higher temperatures have higher vibration of the molecules. So when you pass energy through them, they will be passing information even faster. Through the water, this is how fast the speed of sound will travel through the water. Through the seawater, even faster because there is salt involved. So there's like even more matter. Through the iron, through the rubber. And so through the solid is the fastest speed, through the liquid and through the gas is the slowest. In vacuum, there is no sound travel. And then the velocity has a formula. You don't have to memorize this formula, but there is a formula that it's 330 at 0 degrees Celsius plus 0.6 times the temperature in Celsius. And you will see this in your notes as well. So I'm going to use this information. So before you start looking at the problems, and I probably will mention it in my videos, look at this explanation. Doppler effect. So when you, and it's also in the video that I posted for you online. So Doppler effect. When you hear an ambulance approaching you, the ambulance produces the waves. So the waves go, so here's ambulance and the waves just go like this, right? So they go in all the directions. And you can be, I don't know, like this letter R, and then you hear like that letter R, and then you hear the sound. Or you could be this letter R, and you would hear the sound at the same time. So this would happen when the ambulance is just standing in place and just making the noise. Now, if you are letter R standing, but the ambulance starting to approach you, then every single wave is gonna shift this way. And what happens, actually, let's do this way. So the ambulance is approaching you. So the ambulance is moving toward you. So the center of the wave, the center of ambulance, is going to be moving toward you. So when the ambulance approaches you, you will see the waves coming faster here, but you will see them farther away on the back. So when they're coming faster at you, there's more of them coming toward you. So it's called higher pitch, higher frequency. And then, so more waves per second happens. So the frequency is how many waves per second. So there's more waves per second here. And over here, there's less waves per second happen. So lower pitch. So the ambulance, when it approaches you, it makes a noise like, wee, 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 wee. As soon as it passes you, like, wow, wow, wow. Didn't know if I'm good about it, but I tried. So, and again, there's video that explains Doppler effect. And also there's redshift and blue shift for stars. When I get to the light, I'm gonna do another video for light. I don't want to make sound waves very long, so I'm gonna jump to making light waves. There's some video how old your ears are in the video in the lessons. Please watch that one. That's pretty cool. And please call your parents and probably the dog if you could even ask, or the cat. But the younger children can hear the frequency, lower frequency, that older people cannot hear. And it's usually fun to do in the classroom, but you should try that with other members of your family and present in the room when you try those videos. Then I think next one is going to be the light. So let me stop here, and I'm going to do a different video for the light.